Good evening, ladies and gentlemen. Molecular Biology Review. I'm your host, Ryder. This week, I got something real special for you folks. We're going to talk about chemistry, synthesis of Barbaralones and Bullvalenes made easy by gold catalysis. Sofia Ferrer and Antonio Echavarren, Tarragona, Spain. My dear listeners, I'm sure you're familiar with a certain enigma in chemistry called the fluxional molecule. Well, not all molecules are fluxional, but it refers to a certain kind of crazy-looking molecule. The most well-known is called Bullvalene, and it's basically, here's the picture. Picture's worth 1,000 words. That's Bullvalene. Fluxional molecules are so named because they contain double bonds which appear to leap throughout the molecule due to symmetry. As you're aware, two molecules that are symmetric through rotation can never be distinguished from one another. A similar fact is true about two molecules that differ only by relative positions of double bonds, alternating double and single bonds. The best known example that I can think of is benzene, which contains two possible isomers, yet upon electron pushing to redistribute the double bonds, you're left with a molecule that is identical to benzene, and thus can never be distinguished by any spectroscopic or experimental technique. A similar thing is true with Bullvalene, although in Bullvalene's case, instead of two isomers, there are thought to be 1.2 million degenerate isomers, which can never be distinguished by any spectroscopic method. Barbaralone is a less interesting similar molecule to Bullvalene. Bullvalone is the ketone version of Bullvalene and contains one ketone and two double bonds instead of three double bonds. Barbaralone is related to Bullvalone in that it has one less carbon atom on one of the bridges, thus reducing the symmetry significantly. However, some of the interesting structural properties of the molecule are preserved, such as its fluxional nature. Dr. Echavarren did not wish to synthesize Bullvalene. However, he wanted to synthesize substituted analogs of these compounds. You never know, sometimes substituted analogs are both easier to make and more interesting in terms of drug applications. The current state-of-the-art for creating barbaralone starts from cycloheptatriene carbamoyl chloride. From there, a ring formation is done. This image illustrates well the fluxional nature of barbaralones and by extension Bullvalenes. The two molecules in question, in this case, were produced by a Stille coupling reaction. The authors had noticed that the synthesis of indines, numbers 8 and 9 here, proceeded from the starting material, alkynyl cycloheptatriene, via an intermediate that should be fluxional. It should be a fluxional intermediate that looks like a barbaralone. This reaction was gold catalyzed, so they envisioned that if they stopped the reaction at the intermediate stage by introducing a competing oxidation reaction, they would be able to produce any kind of substituted barbaralones, shown here as molecule number 1. Compound number 1 would be formed by the oxidation of the intermediate form during this synthesis of indines. They succeeded in getting barbaralones by using a gold 1 catalyst and, as an oxidizing reagent, an N-oxide of 3,5-dichloropyridine. The product, 1-phenyl Bullvalone, was obtained in 50% yield, However, 2-phenylindene was still obtained. They also attempted to make Barbaralones via the oxidation of propargyl 1,3,5-cycloheptatriene. However, the reaction proceeded through a 5-exo-dig process and gave the reduced equivalent barbaralane. Barbaralone was homologated to Bullvalene, which, upon reduction with lithium diisopropylamide, yielded Bullvalene in excellent yields. The authors say that this is the most efficient synthesis yet of the parent class of Bullvalenes, despite having only a 10% yield over 5 steps. In summary, aryl barbaralones, Bullvalones, and Bullvalenes were prepared via a gold-1 catalyzed oxidative cyclization.